Hi guys! So we have here our different materials or products that we will use for experiment today. First is our base, and next we have is our glass.
Next, we have baking soda,
And we have our water. And we have vinegar.
and we also have our food coloring.
And lastly, we have coconut oil. Have you ever wondered why oil and water just refuse to get along? Or how retro 1960s lava lamps work without plugging anything into a wall? Today, we're going to build our very own retro lava lamp using basic items you can find right in your kitchen.
I've got a container filled mostly with vegetable oil, and I'm pouring in ordinary tap water. Look closely, the water drops straight to the bottom. Why? Because water is denser or heavier than oil.
Now, let's give it some personality. I'm adding a few drops of bright red food coloring. Notice how the drops falls right through the oil without dissolving? That's because water molecules like water and oil molecules like oil, they just don't mix. But watch what happens when the drop hit the water at the bottom.
Our engine today is a combination of baking soda and vinegar. First, I add a spoonful of baking soda to the jar. Then I'll carefully pour in a little vinegar. When these two substances meet in the water layer, they react and reproduce carbon dioxide gas.
Look at that! As the reaction happens, carbon dioxide gas bubbles to the colored water drops. Those bubbles act like tiny life jackets, dragging the colored water all the way to the oil.
So, to recap, our lava lamp demonstrates three important scientific concepts. First, density explains why water stays below the oil. Second, polarity explains why oil and water do not mix. Third, the chemical reaction between baking soda and vinegar produces carbon dioxide gas, causing the colored water to rise and fall like a real lava lamp. Thank you everyone, and stay curious.
Have you ever wondered why some things float while others sink? Today, we're finding out, and we're starting with our second experiment, the floating egg. Before we begin, our main concept is density. Density tells us how much mass is packed into a certain amount of space. When an object's density is greater than the liquid's density, it sinks. When the liquid is denser than the object can float. Now, let's start with the plain glass water. What if I add an egg here? Depende kung 3 yan. Joke. So now, let's add the egg here. As you can see, the egg sinks down because the egg is denser than the water. Now, let's make a small change and add salt in this cup of water. After that, we have to stir it until they combine and the salt melts or comes in with the water. By dissolving salt in the water, we are increasing its density. Now let's try to put in the egg again. As you can see, it floats now. So cool, right? So, did the egg become lighter? No, the egg stayed the same. We changed the density of the water. Once the salt water became denser than the egg, the buoyant force was enough to keep the egg afloat. And that's our first demonstration of density. But this is only the beginning. Let's see even more surprising effects in our next experiments.
Here we have a clear glass, ice, vegetable oil, and water. Now that we've seen how salt can change the density of water and make an egg float, let's move to our second experiment, which is ice and oil. Before we begin, what do you think will happen when we drop the ice onto the oil? The ice sinks through the oil. This happens because density determines whether an object will float or sink. Ice has a density about 0.992 grams per milliliter, which vegetable oil is generally less dense than ice. Because the ice is denser than the oil, it sinks. Now, let's add some water to our setup. The ice now floats in the water but sinks through the oil. This means that the ice position depends on how its density compares with the density of the liquid around it. So our second experiment shows us something important. Density determines whether an object sinks or floats, and even where it settles, different liquids.